Omar, we will try to have another class this week, inshallah, in which we can do some more kinematics practice and also do Newton's second law of motion. I want to do that before Eid, so that you can use the break to do some questions on that as well. Because otherwise, we won't have enough time left for practice later on. We would need to have consecutive classes, and it would not leave enough time for you to practice. So I would want to have another class before Eid, so maybe tomorrow or on Saturday, in which we do more kinematics practice and also cover the concepts for Newton's second law of motion, so that after Eid or before Eid, a couple of days before that, a couple of days after that, you can do practice on that. And then when we come back, we can do practice in that in our class as well. Okay. So we might have an extra class tomorrow or on Saturday. I will leave a poll on the group to decide that. There's also going to be an S1 class that is scheduled. Yeah, so let's see. Let's see whether it's tomorrow or on Saturday. It looks like it'll most likely be on Saturday. And that will also give you more time to complete the kinematics worksheet, so that if there are any problems that are left, we could discuss them on Saturday then. And then we could also cover the concepts of Newton's second law of motion. All right. Okay, so let's get started then. We were doing kinematics and we were done with pretty much all the concepts that we had in this topic. In the last class, we talked about kinematics graphs. Okay, I hope you've attempted some questions on that and you have come with your problems if there are any. But then mostly the last class was spent on doing this, that displacement, velocity, and acceleration, they're related like this, that if we have displacement, the derivative of that gives us velocity, derivative of velocity gives us acceleration. And if we go from right to left here, the integration of acceleration is velocity and integration of velocity is displacement, right? We learned how we could find velocity and acceleration functions given a displacement function, and then how to go the other way around as well. One thing that was important in particular was, number one, how you can use limits to find displacement from one point to another, and also the difference between the cases when you're finding displacement and distance traveled. Displacement can be found directly by inputting limits. For distance traveled, you have to break down the journey at the points where the direction of the object might be changing. Okay, this was very important to understand, because you will see questions on distance traveled, but they ask you to find distance traveled, and you have to make sure that you keep this in mind, that you check for change in direction and then break your journey at those points when the direction is changing. Okay, I'll have a few seconds break. There's a zone going on here, and then we resume. Okay, so this is what we did. If we had to find distance traveled from one point to another, it was important to check for any change in direction. And how do you do that? By putting v equal to 0. If you get any time values for that, you break your journey down at those points, and then you find displacement for each one of those parts separately. You make them positive and then add them together to find the total distance traveled. Okay, this is what we talked about in our last session. And then, yeah, that was just a summary of that. Now, before we do some more questions now, there's just one small thing that I want to mention that I basically mentioned at the end of the last class as well, that sometimes you will have multiple equations describing the journey of an object. Okay, you'll have multiple equations describing the journey. Let's take an example of that. Let's say we have an object, and this object is traveling at a certain velocity, and the velocity of the object is such that for time between 0 and 5, the velocity is given by 5 times t. For time between 5 and 15, the velocity is constant. And then for the time between 15 and 20, velocity is given by 25 minus t minus 15 whole squared. We've got the velocity function given in 3 parts like this. Okay. Now, given this, first of all, how can we find the acceleration function if we have the velocity function? Finding the acceleration function is fairly straightforward, right? Because we just have to differentiate it, right? V equals 5t. What does that give you? That gives you a equal to 5, right? The derivative of 5t is 5. If you had to find the acceleration function from here, velocity is constant. Now, whatever that constant is, it doesn't matter. The derivative of a constant is always 0. So for the second part of the journey, we know from 5 to 15, acceleration value is equal to 0. And what about the last function? If you had to find the acceleration function for this, we could say derivative of 25 is 0. Derivative of this thing, we have minus outside. We multiply by the power. So that becomes minus 2. We subtract 1 from the power. So inside the brackets, we've got t minus 15. And then this times 1 outside. The derivative of t is 1. So we've got that multiplying outside. That's the acceleration function. So acceleration function, finding the acceleration function in this case is not that difficult. You just have to differentiate each of these equations one by one. Okay, but what if we had to find the displacement function? How do you find the displacement function given this information that the velocity is 5t for the first part, and then similarly for the next parts, it's this and this? Let's start with the first part of the journey, first of all. V is equal to 5t. How do you find the displacement function? Displacement is going to be integral of this, right? Integration of velocity. Let's integrate it. 5t, integration of 5t, that is 5t squared divided by 2. Okay. But then remember, whenever we integrate, we also have a plus c, right? So it becomes 5t squared over 2 plus c. How do you find the value of c now? How do you find the value of c now? Let's assume this object was starting from rest, starting from a point O, and at the point O, the time was 0. So let's say for the starting time, we know that at time 0, the distance from A, or the displacement from O, that was basically 0. So for the first part of the journey, we could say when time is 0, displacement is 0. So we could put that point here. T equals 0, S equals 0, and that will give us the value of C, which turns out to be 0 as well in this case. And the function would be S equals 5t squared over 2. That would be the function that we get from this. That's the displacement function for this part of the journey, for the first part of the journey. Why did we put t equal to 0 and displacement equal to 0? Let's say we know that the particle started at the point when time was equal to 0. And it started from O at that point, and we are measuring displacement from O. That displacement is going to be 0 as well at that particular point. At time 0, displacement is 0. For the second part of the journey now, how do you find the displacement? Now, this is important to understand. If we know that the velocity for the first part is 5 times d, v is equal to 5 times d, what can we say about the velocity for the second part of the journey? The first part of the journey is valid from time equals 0 to time equals 5. Can we find the value of v when time is equal to 5? We can put t equal to 5 here. What value of v do we get? We get v equal to 25. So when time is equal to 5, the velocity value is equal to 25 meters per second. Okay. From the first equation is valid up to 5 seconds in instant. Now, velocity is something that cannot change instantaneously in general. So think about it. Let's say you're going at a speed of 50 kilometers per hour in your car. You're traveling at 50 kilometers per hour. And then you apply the brakes. When you apply brakes, what happens to the speed of the car? Let's say because as a result of applying brakes, it was 50 kilometers per hour earlier. Then it reduces to 30 kilometers per hour. Now, does that happen instantaneously? No, when you apply the brakes, it takes some part of a second or maybe a couple of seconds to reduce the speed from 50 to 30. It does not instantaneously become 30, right? You cannot say that it was 50 and suddenly it became 30. It would first of all go from 50 to 49, 48, 47, 46, and so on, and then eventually reach 30. Yes, it might take very little time, but it is still happening gradually. It's not happening instantaneously. So velocity of a particle cannot change instantaneously. If it was 5 meters per, if it was 25 meters per second at time equal to 5, now for the second part of the journey, time is starting from 5. It is not going to instantaneously change to another number. The value that it would become constant at, it is going to be 25. Now, this is an important concept to remember for problems like these when you have multiple equations. This point that I have here, when time is equal to 5, we call this a boundary point. Okay, it's the boundary of one equation. It's the boundary between one equation and the other equation. At time equals 5, the particle is moving from this equation, switching from the first equation to the second equation, right? At the boundary point, if you are getting v equal to 25 from one equation, from the other equation as well, we should be getting 25 at that time. So that tells us that the velocity for this part of the journey is going to be 25. Okay, now this is 25. What about the displacement function now? What is the displacement function going to look like? V is 25. What's the integration of 25? Integration of 25 is 25t plus c. Okay, that's the integration of 25. How do you find the value of this c now? Remember, this c and this c, they're different. Okay, so do not assume that they're both the same. This is a different equation. It has its own c that's different from the first one. Now the question is, how do you find the value of this c? How do you find the value of this c now? We need some point at which we know the displacement value. Now, we knew earlier that at time 0, displacement is 0, but this second equation is not valid for time 0. It's only valid for time between 5 and 15. So we need some point between 5 and 15 where we know the displacement. Now, do we have any point between 5 and 15 at which we know the displacement that we can use to find the value of c? Think about it. Whatever is the displacement that you have covered in the first 5 seconds, again, just like velocity cannot instantaneously change, displacement can also not instantaneously change to another value. Whatever was the displacement value from the first function, we should get the same displacement value from the second function when time is equal to 5. What that means is, We can use the first equation, and using that equation, we can find the value of displacement when time is equal to 5. So put t equal to 5 here. What value of s do we get from this? 5 into 5 squared, that's 125, divided by 2, that's 62.5. So at time 5, s is equal to 62.5. Now that value for displacement that we found from the first equation at t equal to 5, that's also going to be valid for the second equation now. In the second equation, we can say when time is equal to 5, displacement is supposed to be 62.5. So you input this here, put s equal to 62.5, put t equal to 5, and that is going to give you the value for C, which is going to turn out to be minus 62.5 for the second part of the journey. Therefore, the displacement function becomes 25t minus 62.5. That's what the displacement function becomes for the second part of the journey. Okay. And that tells us another important thing. At this boundary point, just like velocity is not changing, displacement is also not going to change. These are two important things that you need to remember for the cases when you have multiple equations. Remember, at time equals 5, the velocity from the first equation, velocity from the second equation, they should be the same. The displacement should also be the same. Similarly, at time equals 15, the value of displacement that you're getting from the second equation and the value of displacement that you're getting from the third equation, they should be the same. Similarly, the velocities should also be the same. Okay. So using that now, you can also find the displacement function for the last part of the journey now. What would that be? You integrate this thing, that's 25t minus t minus 15 whole raised to the power 3 over 3. Derivative of t is 1, so you can divide by 1 there. That's the integration of this. But then plus c, how do you find the value of c now? Again, what you can do is you can say whatever was the displacement at time equal to 15 from the second equation. So you can use the second equation now. To find the value of displacement when time is equal to 15 and see what that turns out to be. At time 15, what's the value of displacement? 25 times 15 minus 62.5, that turns out to be 312.5. So now for the last part of the journey, we could say when t is equal to 15, because that's the common point between the second part and the third part, we can use t equal to 15. We can say when t is equal to 15, the displacement is going to be 312.5. Using this, now you can find the value of c for this last part, and you can write down the displacement function. Okay. So at the boundary points, which in this case are 5, t equal to 5 and t equal to 15, remember, velocity cannot instantaneously change to another number. Displacement cannot instantaneously change to another number. Acceleration, however, it can sometimes change. For instance, you can look at these equations that we found here. In the first part of the journey, acceleration was 5. That means throughout the first 5 seconds, acceleration is 5. Then from 5 to 15, it becomes 0. So at time 5, it was 5 meters per second square earlier in the first part of the journey, and then it instantaneously changes to 0 in the second part of the journey. And that makes sense when you apply those brakes when you're driving your car. Whatever acceleration it was moving at earlier, when you apply the brakes, what happens is acceleration instantaneously changes, right? It instantaneously becomes negative when you apply the brakes, right? Speed takes time, or velocity takes time to become less, right? It gradually decreases. But acceleration, it instantaneously changes to a different value when you press the brake button, right? Now, for the last part of the journey, if you were to try inputting what happens, and try inputting t equal to 15 in the last part, in the last equation, you get 0 from that. So at time equal 15, acceleration from this is 0. And that's telling you that from this point to this point, acceleration is not changing. So acceleration sometimes can remain the same, sometimes it will be different. It will become clearer if you think of the graph of the velocity function. So that's why I've got the sketch here like this. I've got the x and y axis like this here. Let me sketch this velocity function and see what it would look like. First part is a straight line. V equal to 5t, that's a straight line, right? We can use some point here. We can say when time is equal to 0, v is equal to 0. So this is one point on the graph that we've got. At time equal to 5, velocity is equal to 25. So this is another point that we have. It's supposed to be a straight line, right? Because it's a straight line function, it's a linear function. We can draw a straight line through these points like this. Then the second part is constant, v is equal to 25. So you say it's just equal to 25 from 5 to 15 like this. And then in the last part of the journey, it's a quadratic function. So the last part is going to be a curve now. What is that curve going to look like? It's the completed square form. If you remember your P1 quadratics well, it's a completed square form. It's a quadratic function, first of all, with a negative coefficient of the power 2 term. It's going to be an N-shaped curve like this for that reason, right? But what exactly is that curve going to look like? What part of the curve is going to be here? Are we going to have a curve like this? Is that what it's going to look like? Sometimes we might have graphs like this as well. They're possible, but is it going to be like this in this case? Or is it going to be just some part of the graph? What you can do is you can understand where the turning point lies for this function. The turning point you can see. When does this thing become 0? T equals 15. The number outside is 25. So the turning point of this graph is 15 and 25, right? This is the turning point of the graph. What's that point here? This is the point 15 and 25. So for that quadratic function, this is the point 15 and 25. That means on that graph, we are only going to have the part on the right side, only this part. So the graph looks like this. And the last part of the journey, it's going to be a quadratic curve like this. So when you have to draw quadratic curves, always find the turning point first of all. In this case, since we had a completed square form, we could just look at that and realize what the turning point is going to be. And this is what the last part of the journey looks like now. And now if you think about it, see what's happening to acceleration at this boundary point. This is the boundary point, right? And this is the boundary point. Time equals 15 and time equals 5 and time equals 15. At the boundary point, t equal to 5, remember it's a velocity time graph. Acceleration is given by the gradient of the graph. If you look at the left side of this boundary point, the gradient is 5 here. And if you look at the right side of this boundary point, the gradient is 0 here. So it instantaneously changes from 5 to 0. At the other boundary point, however, the gradient of the graph on the left side was 0. And on the right side as well, it was 0 at this point because it's the turning point. So in the second case, it is not changing. It was 0 earlier, and it was 0 after that boundary point as well. But at the first boundary point, it was instantaneously changing from 5 to 0. So that basically tells us that the acceleration value, therefore, it can sometimes instantaneously change to another value. However, displacement and velocity, they would not change. There's one exception for velocity. Sometimes you will see questions in which you have some collision happening, right? So there might be a particle that's traveling like this, and it hits a wall, and then it suddenly reverses direction. In that case, velocity might change instantaneously, but otherwise, for any other case, you would always say at the boundary point, when you move from one equation to the other, the velocity is not going to change. Okay, so this is an important thing that you need to keep in mind when you look at these questions. We'll have a look at some questions now. At the boundary points, when you move from one equation to the other equation, okay, displacement always remains unchanged. It does not change at the boundary point as you move from one equation to the other. Velocity also always, no, almost always remains unchanged. There's one exception, as we discussed, and that's the case of collision. In that case, you would say that it instantaneously does change to another value. So if it's going in one direction earlier, it would be positive. If it changes direction, it becomes negative instantaneously. Okay. For acceleration, however, we cannot say anything. It may sometimes change, it may not change. We can't be sure about it. Okay, we cannot be sure about it. Okay, so for acceleration, we're not going to assume something. Sometimes they will ask you in the question, does the acceleration instantaneously change or not? So you would find acceleration from one equation, find acceleration from the other equation, and then use that to basically tell them if it's changing instantaneously or not. But for displacement and velocity, know that it is not going to change instantaneously, except velocity in case of collision. In general, they do not change. Okay, all right. Yes, Umar. So Umar is saying, could we draw this graph like this, that we know that we are doing 25 minus something. So we know that the velocity is always going to be less than 25. So the graph, therefore, we know cannot go above 25. So it has to look like this. However, it's still important to figure out that this point is the turning point, because you could have two different shapes in that case as well, which might not be very different, but they are still different. You could have a graph like this, where this is not the turning point, right? In this case, the gradient at this point would not be becoming zero, but a more accurate drawing would be that you clearly draw it like this, such that that point looks like a turning point. And that can only be done if you first find that turning point. And in this case, that does turn out to be at that point 1525. Okay, so that's just a small point that I wanted to make before we move on to some questions. Now, let's have a look at some questions. You can let me know the problems that you have. Okay, so I would prefer doing questions on differentiation, integration, and graphs, first of all, because we've done others before. But let's start with this one, question 54. And then if it's not one of these questions, I would want to do more of graph questions and differentiation and integration questions. So if you have those with you right now, let me know, and I would want to discuss them first. Okay, so you can let me know in the chat the questions that you want me to do. So you can start with them. Kinematics worksheet, the second one that was uploaded. Okay, Omar, what I'm doing is, since it's not that, what I'll do is, since I do have other questions as well that you're posting, I'm copying it here. Let's just do a couple of other questions first. So if you have done some graph questions and differentiation integration questions as well, since that's what we've just talked about, and also in the last class, let's do some of those first, and then we could do this next. So we will do this today. But after doing a couple of other questions first that involve graphs and differentiation integration. So I'm copying this here. Let's have a look at this. Let's come back to this in a few minutes. in some time in 20-30 minutes. So we're saying from this other worksheet, question 5. Okay. Okay, let's start with this one because this does involve those equations. Let's have a look at this. Question number 5. Let's do this one first. Shiva, is this the one that you're asking about? Okay. Okay, let's have a look at this now. It says a particle P starts from rest at O and travels in a straight line. The velocity at time t is given by this function for time between 0 and 3, and velocity is equal to this function when time is greater than 3. So again, velocity is defined in two different parts for different time intervals. In the first part, it says, find the distance traveled by P in the first 3 seconds. Distance traveled by P in the first 3 seconds. V is equal to 8t minus 2t squared. Remember, whenever we have to find distance traveled, always check first if the direction is changing or not, because you would not know in the exam if it's changing or not. So you should always check that. Don't just assume that it mostly does not change, so we can just directly input limits. That will make you do errors in the exam. Make it a habit to always check for the change in direction. How would you do that? You would put v equal to 0. And that gives you 0 equal to 8t minus 2t squared. Let's see what we get from this. We can take 2t common. That leaves us with 4 minus t inside. So either t equals 0 or t equals 4. At 0, the journey is starting. So at that point, velocity is 0, first of all. That's okay. And then the second time velocity is 0, according to this equation, is at time equal to 4. This equation is not even valid when time is equal to 4. It's only valid for the first 3 seconds. So that means there is no change in direction. There is no change in direction for the first 3 seconds. Okay, you always have to check for this first. If there was a change in direction, you would have to break your journey down at that point. Okay. Now, in this case, there's no change in direction. So what do we do then? We say this is the velocity function. We have to find distance traveled from one point to another from time equals 0 to time equals 3. We can just integrate it now. So that's 8t squared over 2 minus 2t cubed over 3. Input limits in this. 4t squared minus 2t cubed over 3. Input limits from 0 to 3, and that will give you the result. You can see what that turns out to be. Input 3 and 0. Let's input 3 first of all. That gives us 4 into 3 squared minus 2 into 3 cubed divided by 3. Subtract from this the case when you input 0. That's just going to become 0. What's the result that we get from this? 18. Thank you. So that's the result that we have. That's the distance traveled in the first part of the journey. Fairly straightforward. That's 4 marks. That's what you were looking for in the first part. Okay. Now it says find an expression in terms of P for the displacement of P from O valid for time greater than 3. So now we're looking for a displacement function. Remember, in these cases, we do not use limits. Okay, we do not use limits in these cases. So how do we deal with this now? The velocity function is given by, for the second part of the journey. Remember, we're looking for a displacement function for the second part of the journey, right? So that velocity function is given by 54 over t squared when time is greater than 3. We want to find the corresponding displacement function. How do we do that? How do we go from velocity to displacement? We integrate this. Let's first of all write down in the power form in the numerator. So it becomes 54 t raised to power minus 2. And now we can integrate it. 54 remains as it is. Add 1 to the power. So it becomes t power minus 1. Divide by that new power. But remember, whenever we are not inputting limits and we are integrating, we always have a plus c. Do not forget that. We're going to have a plus c here. Okay. So s equals minus 54 over t plus c. That is what the displacement function look like. And now the question is, we do not know the value for C, right? We don't know the value for C. Do we have any point at which we know the value for displacement? Do we have any point in the second part of the journey when time is greater than 3 at which we know the displacement? They haven't given anything in the question, but in the first part, we found that the displacement covered in the first 3 seconds is 18. So we can use that here because we know, we just discussed that displacement always remains unchanged at the boundary point. When you go from one equation to the other equation, it does not instantaneously change to another value. So if it was 18 earlier, for the second part of the journey as well, for at time equal to 3, the displacement value is still going to be 18. So we can input that number here, find the value of C from this and see what that gives us. 18 equals minus 54 over 3 plus C. What's the value of C that we get? 54 over 3 is 18. So that goes to the other side, becomes 36, right? So the displacement function that we were looking for, therefore, is minus 54 over t plus 36 when time is greater than 3. That's the displacement function. No, there's something wrong here. Time was 3. So when we input time 3 here, we should be getting 18. Are we getting that? Okay, yeah, this is fine. This is fine because we just need to check that at time 3, it should give us 18, and it is giving us 18. So that is correct. So that's the displacement function that we've got. And that's what we were looking for. That's the final answer. What's 54? Okay, so that's fine, right? Yeah, okay. So that was the second part. Now let's look at the third part. Find the value of V when the displacement of P from O is 27 meters. We want to find the value of velocity at that point when the displacement is 27 meters. So now we've got the displacement function, right? Once we have the displacement function, what we can do is we can find that time instant when the displacement is 27, right? So they gave us that the displacement at some point is 27. We need to find the value of V at that point. We know that this is the velocity function. 54 over t squared. Okay, by the way, how do we know that we have to use this velocity function and this and not this velocity function? Remember, we already showed in the first part, in the first 3 seconds, the displacement was 18. If displacement is 27, that's definitely happening after 3 seconds, right? So that is why I'm only considering the second equation, right? The second equation is V equal to 54 over t squared. This is valid when time is greater than 3. We need to find the value of velocity when the displacement is 27. So what we can do is we can put S equal to 27 in the first equation, and that gives us 27 equal to minus 54 over t plus 36. And that's going to give us some value for t. Let's see what that is. 54 over t equals 9. And t equals 54 over 9, which is 6. Put that value of 6, put that value of t in the other equation for velocity. That's 54 over 6 squared. That's 54 over 36. That is going to be 1.5. 1.5 meters per second. That's the velocity function that we have. And that's the velocity value that we have at that point. Okay, so the first and third part, they were fairly straightforward. In fact, the second as well, once you understand what happens at the boundary points, the displacement and velocity numbers, they remain unchanged. Okay, I hope that makes sense. Let's move on to the next one now. Let's move on to the next one. Question number 4 from that second worksheet. Okay, let's try this. Okay, let's have a look at this next. And then we do 54 after this, and then any other questions that you guys have. Maybe at least one graph question, because we haven't done any of them. If there are any problems, of course, although those questions are fairly straightforward generally. Okay, question number 4 from the second worksheet. Let's try this. This is from May, June 2022, paper 4.1, question number 6. Let's have a look at this. It says, a particle starts from a point O and moves in a straight line. The velocity of the particle at time t seconds after leaving O is given by this. We have the velocity function given. We first need to verify that the particle returns to O when time is equal to 2. If the particle returns to O, that means it returns to its starting point. That means that the displacement becomes 0 at time equals 2. So we need to show that the displacement when time is equal to 2 is equal to 0. Okay, now how do we show that? We have a velocity function, right? How do we go from velocity to displacement? We can use integration. Let's integrate the function. V is equal to k into 3t squared minus 2t cubed. That's the velocity function. Let's integrate this. K is a constant that remains as it is. You integrate this part. This becomes 3t cubed over 3 minus 2t raised to the power 4 over 4. Now, do we put a plus c there or not? We are looking for value of displacement. At what point? At time equals 2. So we can use limits. We can use limits from 0 to 2, right? And because we're looking for displacement from time equals 0 to time equals 2. So we can input these limits, right? And now we need to verify that the displacement becomes 0 at time equals 2. Let's input these limits and see what that gives us. K times 3 into 2 cubed divided by 3 minus 2 into 3 raised to the power 4, 2 raised to the power 4 divided by 4. Subtract from this the case when you input t equal to 0. That will make both of them 0. Let's simplify this. 3 into 8, that's 24 over 3. 8 minus 32 over 4, that's also 8. So this becomes 0. K times 0, that's 0. Displacement turns out to be 0. And that's it. That's what you have to prove. Since the displacement is 0, that means the particle returns to O because displacement is 0, right? So this is a 0, this is an O. So it returns to O because displacement becomes 0. That proves it. Okay. Now the second part says, it's given that the acceleration of the particle is minus 13.5 for the positive value of t at which v equal to 0. Okay. Find k and hence find the total distance traveled in the first 2 seconds of the motion. Let's think about the second part now. It says the velocity function is that same function, v equal to this. That's the velocity function. Now, what we have to do is, we are given that the acceleration is this at the positive value of t at which v is equal to 0. Okay, now understand the question statement. There is some point at which velocity is 0. At that point, acceleration is minus 13.5. Now, first of all, let's find that time instant when velocity is 0. How can we find that? We have the velocity function. Let's input v equal to 0 in this and see what that gives us. V equal to 0. When we put v equal to 0, we get 0 equal to k into 3t squared minus 2t cubed. K will go to the other side, becomes 0. And then we can take t common from the right side, that t square common from the right side. That leaves us with 3 minus 2t inside. That means either t square equals 0 or 3 minus 2t equals 0. T equals 0 or t equals 3 over 2, which is 1.5. We're getting two values of t when velocity is 0. One of them is 0. That's not what we're talking about. They said the positive value of t. So this is the value of t that we're talking about. At this value of t, they're saying acceleration is equal to minus 13.5. That's what they've told us in the question. Okay, at this particular point, acceleration is supposed to be minus 13.5. So what do we do now? We say we've got the velocity function. The velocity function is k into 3t squared minus 2t cubed. Let's find the acceleration function from this. How do we do that? We differentiate it, right? Find the derivative of this. It becomes k as it is. K is a constant that remains as it is. You find the derivative of this. What's that? 6t minus 6t squared, right? That's what we get. 2 into 3, that's 6. And 3 into 2, that's also 6. But the power becomes 2 in that case. Now, this acceleration, they're saying when time is equal to 1.5, the acceleration is supposed to be minus 13.5. We input those two values here, and that is going to give us the value for k. Let's see what that turns out to be. Minus 13.5, that equals k into 6 into 1.5 minus 6 into 1.5 squared. And we can find the value of k from this. You can see what that is. Has somebody done this? What's this value? 9 minus 6 into 2.25. Okay, is it coming out to be 3? K is 3, right? Okay, good. So that's the value of k that we get. That was part B. Yeah. Now we need to find the total distance traveled in the first 2 seconds of the motion. So the value of k is 3. Given this, find the distance traveled in the first 2 seconds. How do you find distance traveled? Remember, whenever you're asked for distance traveled, you again always have to check if there is any change in direction. If you think about it, we've already done that. We put v equal to 0, and at v equal to 0, we got time equals 1.5. We want to find distance traveled in the first 2 seconds of the motion. Velocity is becoming 0 at time equals 1.5. That means the direction is possibly changing at 1.5. So we have to break the journey down into 2 parts. The velocity function now is, since k is equal to 3, we can say the velocity function becomes 3 into 3t squared minus 2t cubed. Or in simplified form, that would be 9t squared minus 6t cubed. That is the velocity function. We want to find displacement, but since we know the direction is changing when time is 1.5, we have to break it down into 2 parts. We say, let's consider one part from 0 to 1.5, and then the second part of the journey from 1.5 to 2 seconds. Okay, so we break it down like this. Let's integrate this function 9t cubed over 3. That becomes 3t cubed minus 6t raised to power 4 divided by 4. That would be 3 t raised to power 4 over 2, right? 6t raised to power 4 over 4, that simplifies to 3 over 2 times t raised to power 4. That's the integration, input limits from 0 to 1.5. And then you do the same thing from 1.5 to 2 separately. Okay, so you have to break the journey down into 2 parts because the direction is changing at 1.5, and you evaluate these two separately like this. So what we do now is we input 1.5 first of all, 3 into 1.5 whole cube minus 3 into 1.5 raised to power 4 divided by 2. Subtract from this the case when you have t equal to 0. When t is equal to 0, this whole thing becomes 0. And that's going to give you some value. You can see what that is. Then you input 2 and 1.5. So 3 into 2 raised to power 3 minus 3 into 2 raised to power 4 divided by 2. Subtract from this the case when you have t equal to 1.5, that will be 3 into 1.5 raised to power 3 minus 3 into 1.5 raised to power 4 divided by 2. And that gives you the second part, the displacement for the second part of the journey. You can see what that is as well. Has somebody done this? Okay, Seren, I'll explain that. Just give me a minute. Let me just write down the final result. How to put the correct signs? What does that mean? You're not using any signs here as such. They gave us that acceleration is minus 13.5. So that's minus 13.5. Just put that same value. You have to care about the positive negative values when we're talking about constant acceleration formulas generally. There we have to be careful. But here, we just use the positive negative that we're given. What are the values that we're getting? The first part and the second part? What are the values that we're getting? Three into 1.5 raised to power 3 minus 3 into 1.5 raised to power 4 divided by 2. Okay, that's the first part. That's giving me 81 over 32. Is that correct? And then the second part is when this becomes 2 first of all. And this also becomes 2. Okay, so this is giving me 0. And then we have minus that same number, 81 over 32. So we've got minus 81 over 32 from here. Oh, we could actually use the first part to do this as well. I'll explain. But in this case, we've done that anyway. So let's just do this like this. 81 over 32 and minus 81 over 32. What's the total distance traveled? What's the total distance traveled? The distance traveled is 81 over 32. We first of all make both of those numbers positive, right? And then we add them up together. 81 over 32 plus 81 over 32, that's 162 over 32, which will be 81 over 16. And that's it, 81 over 16. That's the result that we get from this. 5.06. That's the total distance traveled by this. Okay. That's the total distance traveled until this point, 5.06. Okay. Now, what does this journey look like? It's basically like this. At time 0, the velocity was 0. And then when it became positive, the particle started moving in some direction. Was it positive direction or negative direction? And let's try that. If I input 9 into 1 squared minus 6. Okay, that's positive direction, basically. Okay, so that's what the journey of the particle looks like. So basically, it started from the point O. It went to the right side until t equals 1.5. And then it started its return journey and came back to the same point again at time equals 2. At t equals 1.5, the particle changes its direction, right? Because at that point, velocity was equal to 0. At that point, the direction was changing, right? When the direction was changing, time was 1.5. So it went 81 over 32, whatever that number was. It would be 2.53 meters. It went 2.53 meters to the right side and then 2.53 meters to the left side. So the total distance traveled is 5.06. Okay. You could make this a bit more efficient by considering what you did in the first part. In the first part, you proved that the particle returns to O when time is equal to 2. So we know that at time equals 2, the particle would be at the same position again where it started from. So we could also just do it like this. We could say from 0 to 1.5, the particle is traveling a distance of 81 over 32. So it's going in the right direction and it's traveling this much distance, 81 over 32. And we know already that at time equals 2, the particle would be coming back to its original position. So whatever distance it covered to the right side, it'll be the same distance that it'll cover to the left side. So we would already know that this is supposed to be 81 over 32 already. We could, if we were able to figure that out earlier, we could just skip this part of the working and directly say that we could just multiply this number by 2 because we know the distance that you're traveling in one direction, and the return journey, it will be the same distance traveled as well. The displacement in this case is going to be 0, yes. The displacement is going to be 0, but the distance traveled is going to be 5.06, right? Okay, now, why do we need to break this journey down? We did that in the last class, if you remember. Whenever we have to find distance traveled, we always check if the direction of the object is changing. And how do we do that? By putting v equal to 0. Because if the direction is changing, displacement and distance traveled would be different. So if a particle is going towards right and then it's coming back to the left, let's assume that this distance is 300 meters and this is 200 meters. The total distance traveled by the particle is 500 meters. If we do not break this journey down, so let's say this is time 0, this is time equal to 5, and this is time equal to 8. If you don't break this journey and you directly input limits 0 to 8, the equation is going to give you this number. It's going to give you just 100. That's the displacement from A to C if you directly input limits 0 to 8. So we have to break the journey down. If we're looking for distance traveled, we have to break the journey down at the points where the direction is changing. So the direction is changing at time equals 5. We do it in 2 parts. We first of all input limits from 0 to 5, and then we input limits from 5 to 8. One of them is going to give us a positive result. The other is going to be negative because in the second part, displacement is negative. We first make them positive. We add them up together. That gives us the total distance traveled. That will be 500 meters in this case. If we were not to break this journey down, you would just get 100 meters. That would not be distance traveled. That would be displacement. And that's not what we are looking for here. Okay, so that's what we discussed yesterday. Whenever you have to break this, whenever you have to find distance traveled from one point to the other, break the journey at the points when v is equal to 0, because the object may be changing its direction at that specific point. So it's important to change. It's important to break the journey down at those specific points. Okay. All right. Let's move on to the next question. Is this clear to everyone? Any problems with this? Any questions on this? Okay, if v is equal to 0, how come acceleration is minus 13.5? Where exactly? Okay, so you are saying at this point, velocity is 0. How can acceleration be minus 13.5? That's a good question. Since the particle you're saying it's at rest, the acceleration should be 0 as well because it's at rest. It's at instantaneous rest, right? It's at rest just for a fraction of a second or just for an instant, right? So its velocity was, let's say, some positive value earlier, then it became some negative value. In the middle, there is just some specific instant at which the velocity is 0. But overall, it's decreasing, right? It's going from positive to negative. That's why acceleration is negative, because the change in velocity is negative at that point as well. Right? It's not that the object is at rest for some length of time. It's only 0 for a specific instant. It's instantaneously at rest. So that's why acceleration can be some negative number here. because it's going from positive to negative. Is that clear, Umar? Okay, good. Let's move on to the next one now. Let's do that question that you asked from the other worksheet. Question number 54. Let's have a look at this. Okay, if anyone has any graph question after this, please let me know if you want to ask about that, because that might be one last question that we do today. If you have any, if not, let's see how much time we have. We could do another question. If you have more questions, we could do them in one last class that we would have in kinematics. Most likely this week, one extra class in which we will do some more practice questions in kinematics and also cover the concepts of Newton's second law of motion. Okay, let's have a look at this quickly. It says a particle is projected from a point P with initial speed u up a line of greater slope PQR of a rough inclined plane. It's a rough surface. Okay, it goes like this. It's an inclined surface. It's projected with an initial speed of u meters per second. So its initial speed of projection is u meters per second. PQR is the slope. So there are some points P, Q, and R on this. P, Q, and QR are both equal to 0.8. So we can say there's some point P here. There's another point Q on this plane. And there's a point R on this plane, such that the distance P, Q, and QR, they're both the same. Okay, now the particle takes 0.6 seconds to travel from P to Q and 1 second to travel from Q to R. Show that the deceleration of the particle is 2/3 and hence find u, giving your answer as an exact fraction. Okay, so what do we know about this journey? What exactly do we know about this journey? We have two parts of the journey. We have P to Q part of the journey, and then we have Q to R part of the journey. The particle is moving up the slope, right? So we can consider this direction as positive direction, right? We're considering up the slope as positive. Now, if that's the positive direction that we have, then what information do we have about the particles? We know the initial velocity. The initial velocity is u for P. At the point P, the initial velocity is u. Okay, what else? We know that the time taken in this part of the journey is 0.6. And what else? We know the displacement, that is 0.8. Okay, similarly for the second part of the journey, we know the time taken, that is 1, displacement, that is 0.8. And let's see what other information do we have. Let's just give me a second. I'll be back in a moment. Somebody calling me. Okay, so we have the time taken for each part of the journey. From P to Q, it's 0.6. From Q to R, it is 1. And we need to first show that the deceleration of the particle is 2/3, and hence find u, giving our answer as an exact fraction. Okay, now how do we think about this? What other information do we have about Q to R part of the journey? We know the time taken, we know the displacement. What else? Do we have initial velocity? No. Do we have final velocity? No. Do we have acceleration? No. Now, when you have two parts of the journey like this, remember what we talked about earlier. What we want to do is, we want something common between the two parts, right? We want something common between the two parts. The other quantities, they should be common. Now, acceleration can be common between the two because, right, the particle is going up the plane. Whatever other forces acting on the particle, they are going to be the same at during PQ part of the journey and during QR part of the journey. So acceleration is constant. Acceleration is common between them. But this U is not common. Initial velocity for the first part is different. Initial velocity for the second part is different. And if we use another variable here, for example, initial velocity for this part, let's say that's VQ, that will be too many unknowns that we would have. We would have A, U, and VQ. We have two equations, three unknowns. That will be too many unknowns to work with. Remember what we do in problems like these? We discussed another very similar question to this earlier. What we can do is, instead of considering PQ and QR, we could say, let's consider P to R instead, right? We could consider P to R instead because that will make sure that the initial velocity for both parts that we're considering is U. And that reduces the number of unknowns that we've got. We have U and we have A. We have only two unknowns. Two unknowns, we can make two equations. And using these two equations now, we can find the values of U and A. How can we do that? Which equation connects these four things? U, T, A, and S is S equals UT plus half AT squared. We can use that. Make two equations, solve them simultaneously, and you would get the result. Okay, so that's fairly straightforward after this point. S is for the first part of the journey. Let's actually just change these values as well now. From P to R, what would be the total time taken? From P to Q, it was 0.6. From Q to R, it's 1. So the total time, therefore, would be 1.6. The total displacement, that would be 0.8 plus 0.8, that's 1.6 as well. So this is 1.6 meters, this is 1.6 seconds. So now we can make two equations. For the first part of the journey, we can say S, which is 0.8, that equals U times T, which is 0.6, plus half into A, which is A, into T squared, which is 0.6 squared. That's one equation. And the other equation is 1.6, that equals U, which is U, into T, which is 1.6, plus half into A, into T squared. And that should give you the result. You can see what that is. 0.8 equals 0.6 U plus 0.36 over 2, that will be 0.18 times A. And the other equation is 1.6 equals 1.6 U plus 1.6 squared. That's, I'm not sure, 2.56. Okay, 2.56 divided by 2, that would be 1.28 times A. Solve these two equations simultaneously. You would get A equal to minus 2 over 3 from this. And then you would also get the value for U. What's the value of U that you get? What's the value of U that we get? If A is minus 2 over 3, of course, that means that deceleration, therefore, they asked for deceleration. Deceleration is 2 over 3. Okay, and then you can find the value of U as well. Make sure to show this working. I'm just saving time right now so that we can do the second part as well. But you have to show the working for this. What's the value of U that you would get? 0.8 minus 0.18 times minus 2 over 3. That's, and then whole divided by 0.6. That's 23 over 15. The value of U is 23 over 15. No? Okay, maybe I did something wrong. 1.6 minus 1.28 times minus 2 divided by 3. I'm using the other equation now. That's 1.6. Well, that's correct, I think. Yeah, so yeah, it's 23 over 15, right? Okay, so 23 over 15, that's the value of U that we're getting, 23 over 15. They said, give your answer as an exact fraction. So don't use decimals here. The question specifies that you have to give your answer as a fraction. So do not use decimals here. And that's it. That's the first part. That's what you have to do here. The second part says the plane is inclined at 3 degrees to the horizontal. Find the value of the coefficient of friction between the particle and the plane. Well, this is actually Newton's second law of motion question. The second part, we have not done that yet. But since we're doing it now, I'll just complete this anyway, because I assume you would have done that at least once before at some point when you covered the concepts at school, maybe, or maybe some of you might be taking physics. So you might know at least this one formula that we've got. The Newton's second law of motion, that is basically the resultant force is equal to mass into acceleration. Okay, I'm not sure if I've mentioned this before in this course yet or not, but that's the next topic that we will be doing. This is one formula that we have in this topic, Newton's second law of motion. Resultant force equals mass into acceleration. Now, how is that going to be used here? Whenever we have forces and acceleration coming together, whenever we have forces and kinematics coming together, this is the formula that basically connects both of them. Okay, it connects both of these things, forces and acceleration. So that's what we're going to use here. The question says, given that the plane is inclined at 3 degrees to the horizontal, let me represent that here. It's inclined at 3 degrees, so this angle is 3 degrees. It does not look like 3 degrees on my diagram, but that's okay. It's just for our own reference. That's the angle 3 degrees. Find the value of the coefficient of friction between the particle and the plane. Okay, now in this case, we have to think about the forces that are acting on the object, because about coefficient of friction, all we know is F is equal to mu r, right? When an object is moving, when an object is in motion, F is equal to mu r. Friction is at its maximum value, both when the object is in motion and also at limiting equilibrium. We're not talking about equilibrium anymore. We're talking about moving objects. F is equal to mu r when objects are moving as well. In this case, we've got friction, we've got reaction. So we have to do something with forces, right? Let's represent all the forces acting on the object in this case. So let's represent the object somewhere here. Let's say we've got this object here. And what are the forces acting on this? There will be weight of the object that acts vertically downwards. Do we have any information about that? About the mass of the object? No. Okay, so we can assume that the mass is m, then the weight would be 10 times m, right? Okay, then we have normal reaction that acts in this direction. The particle is moving up the plane. So where does friction act? Friction acts opposite to the direction of motion. This is the direction of friction. And what else? Do we have any other forces given in the question? Well, not really. There's no other force that's given in the question. So these are all the forces that are acting on the object. What are the forces that we have to think about ourselves? Weight, normal reaction, friction, and tension. Tension, there's no tension here as such, because there's no string involved. These are all the forces. Let's resolve weight. There will be two components of weight, one in this direction and one in the other direction. If this angle is 3 degrees, we've done this multiple times before, this angle is also going to be 3 degrees. So that means this component is 10m into cos of 3, and the other component is 10m into sine of 3. Now, the object is moving along the surface in this direction. That's the direction of motion. There is no motion perpendicular to the surface. Remember, we've discussed this before as well. Even though the object is moving up the plane, we are not going to assume a forward force ourselves. Okay, unless it's given in the question, we don't assume it ourselves that there is some forward force because the object is moving in the upwards direction. The particle was projected from the bottom and then it was released, right? So because of that initial speed of projection that was given to it, u, which was 23/15, so we gave it some initial speed. Because of that initial speed, it keeps moving upwards for a while until it reaches its maximum point, and then maybe it will start coming down. But while it's moving, there's no forward force acting on this. I gave you this example last time. If we throw a ball in the upwards direction, we don't go with the ball ourselves, right? We just release it and then it keeps going up for a while because of that initial speed that we gave us. But after we have released the ball, there's no force acting on the ball anymore. So there's no forward force. It's just moving in the upward direction up the plane because of that initial speed, initial push that we gave us. So don't assume that there's a forward force at yourself. Okay. Okay, so these are the forces that are acting perpendicular to the surface. The objects are going the forces are going to be equal to each other. So reaction and 10m cos 3, they're going to be equal to each other because there's no motion in this direction. R is equal to 10m into cos of 3. And then along the surface, since the object is moving in this direction, we say resultant force equals mass into acceleration. What's the forward force? The forward force is 0. Backward force is F. And 10m sine 3, this is the resultant force. Forward forces minus the backward forces equals mass into acceleration. What's the acceleration? We found that in the first part. Remember, it's minus 2 over 3, not plus 2 over 3. So it's minus 2 over 3. That's one equation that we brought. Since the object is moving, we know that friction is going to be at its maximum value. So F equals mu I. We can say 0 minus mu times R minus 10m into sine of 3. That equals minus 2 over 3 times m. So 0 is already eliminated, in fact. So that's just a 0 minus mu R. And now minus mu into R, let's put that here, minus mu into 10m into cos of 3 minus 10m into sine of 3, that equals minus 2 over 3 times m. We can divide the whole equation by m, right? So m gets cancelled basically because of that. And we're left with minus mu. We can also multiply this by minus. So minus also gets eliminated. So we have mu into 10 cos 3 plus 10 sine 3 equals 2 over 3. And we can find the value of mu from this. That turns out to be 2 over 3 minus 10 sine 3 whole divided by 10 cos 3. And that's the final answer. You can see what that turns out to be. What's the value of mu that you get? What's the value of mu that you get from this? That's what we were looking for, right? The coefficient of friction. That will give you the result, 0.014. We want at least 3 significant figures. At least 3 significant figures. What would that be? At least 3 significant figures. Two over 3 minus 10 sine 3 divided by 10 cos 3. And that gives us the result. That's 0.014350. So that rounds off to 144. That is our final answer. That's the coefficient of friction that we were looking for. Okay, to 3 significant figures, that's our final answer. And that's how we do it. Question 83, keep that in mind for the next class. Okay, we will end our class today at this point. I'll see you again in the next one. In the next class, most likely on Saturday, I'll confirm that in the group as well. When we're going to have the next class, most likely Saturday, the extra class this week, we will complete any remaining worksheet questions that you guys might have, and also cover the Newton's second law of motion, so that during the Eid break, when we would not have classes, you can complete that or attempt as many questions as you can from the Newton's second law of motion worksheet as well. So when we come back, we can practice that more. Okay. Umar, let's discuss this on the WhatsApp group. I'll leave a poll. There's actually going to be an S1 class tomorrow as well, but because of which there is going to be a problem doing it tomorrow. It's difficult to do it tomorrow, but we will check this. We will confirm this after discussion on the group. I'll have to check with the S1 group first of all when they want to have a rescheduled class, because I'll be missing today's class. So I have to reschedule that as well. So I cannot say anything for sure. Okay. Most likely it's going to be Saturday. If that can be changed, I'll let you know. Okay. All right. I'll see you again in the next class then. Allah Hafiz.